Hey class, today I will be teaching you about Lambda Calculus and telling you why you should care about it. First, let's go over some historical context. In 1928, mathematician David Hilbert posed a question known as Entscheidungsproblem, problem, which basically asked, is there such thing as an unsolvable problem? Hilbert thought no, but then in 1936, these two computer scientists, Alan Turing and Alonzo Church, independently proved that yes, there is such thing as an unsolvable problem. How did they do this? Turing came up with a model of computation known as the Turing machine. I'm not going to go too in-depth into Turing machines in this video, but I want to give a brief overview. A Turing machine points to a particular spot on an infinite tape. It has a state, it can move left or right on the tape, and it can also read or write on the tape. The behavior of the Turing machine depends on its state and the input it reads on the tape. Church came up with a model of computation called Lambda Calculus. If you have one takeaway from this video, the thing I want you to remember is that Lambda Calculus is function definition and application. There are three types of Lambda expressions. The first is variable, which is any symbol or sequence of characters besides lambda or parentheses. The second is function definition, which looks like this. The way to think about function definition is that the variable is the parameter of the function and the expression is the function body. The third type of Lambda expression is function application, which looks like this. The way to think about function application is that we apply the first expression to the second expression. Something I would really like to emphasize is that due to the recursive nature of lambda expressions, you can have lambda expressions in other lambda expressions. Let's look at some lambda expressions. Here are some valid lambda expressions that have the same format that we just saw on the previous slide. Here are also some valid lambda expressions, and you'll notice that here we have lambda expressions nested inside of other lambda expressions. Now it's your turn. Which of these are valid lambda expressions? I encourage you to pause the video to try this out for yourself. Here are the answers. The first expression is a valid variable. The second expression is a valid function application. The third expression is not valid because it is missing parentheses. The fourth expression is not valid because it is missing a dot between x and y. The fifth expression is a valid function definition. The sixth expression is not valid because it is missing a right parenthesis. Lastly, the last expression is really long, but it is a valid function application. Now we know what lambda expressions are. How do we evaluate them? Let's say I have a lambda expression that looks like this. This is a function application where we have a function definition as the first expression and some other expression as the second expression. When you see this, I want you to think, everywhere I see var in expression 1, replace it with expression 2. For example, if I have lambda x.x applied to cat, then I think, everywhere I see x in x, I replace it with cat. So this expression reduces to cat. If I have lambda x.y applied to cat, then I think, everywhere I see x in y, I replace it with cat. X does not appear in y, so this expression reduces to y. If I have lambda x.lambda y.xy applied to cat, then I think, everywhere I see x in lambda y.xy, I replace it with cat. Then this expression reduces to lambda y.caty. This process of evaluating lambda expressions is called beta reduction. Having nested lambda expressions means that we might be able to beta reduce more than once. Take this example. We have lambda x.lambda y.x applied to cat, applied to dog. How would we go about beta reducing this? Recall from the earlier slide that if we see an expression, we think, everywhere I see var in expression 1, replace it with expression 2. The problem is, our expression doesn't look like this. However, if we look at just the first sub-expression of our function application, we can see that this sub-expression actually does match the format we are looking for. Then, we can beta reduce the first sub-expression. Remember, think. Everywhere I see x in lambda y.x, replace it with cat. Then this sub-expression reduces to lambda y.cat. Going back to our full expression, we can see that after one beta reduction, our expression is now lambda y.cat applied to dog. Then we think, everywhere I see y in cat, replace it with dog. Y does not appear in cat, so after two beta reductions, our expression reduces to cat. When we can no longer reduce an expression, we say it is in normal form. Now it's your turn. Can you beta reduce the following lambda expressions? I encourage you to pause the video to try this out for yourself. I'm not going to go over the full beta reductions, but here are the answers. I do, however, want to take a closer look at the last expression. When we see this expression, we want to think, everywhere I see x in xx, replace it with lambda x.xx. But when I do that, whoa! We get the original expression. In fact, if I keep beta reducing, I'm going to keep getting the same expression. This means that this expression has no normal form. So, why should you care about lambda calculus? Remember when Hilbert asked, is there such thing as an unsolvable problem? Church used lambda calculus to show that, yes, there is such thing as an unsolvable problem. We didn't really go into why this is in this video, but if you're interested, you should check out something called the Church-Turing thesis. Also, lambda calculus is the basis of many functional programming languages such as Lisp, Clojure, OCaml, Racket, and Hi. You'll see that several of these even prominently feature the lambda symbol in their logos. Let's summarize what we've learned today. We learned that Alan Turing and Alonzo Church both showed that there is such thing as an unsolvable problem. Turing showed this using Turing Machines, and Church showed this using lambda calculus. We learned that the core of lambda calculus is function definition and application. The three types of lambda calculus are variable, function definition, and application. We also learned how to beta reduce, with the main idea being, everywhere I see var in expression 1, replace it with expression 2. We learned that an expression is in normal form when we cannot beta reduce it anymore. Lastly, we learned that lambda calculus is the basis of many functional programming languages. As always, thank you so much for watching. This is your CS Professor of Fun.